Hello everyone. Today I will be presenting about efficiency through concurrency as Nishadi mentioned earlier. In this session, I will be talking primarily about parallelism, multi-threading, thread safety, uh, asynchronous programming, among other. So let's get started. As software developers, our ultimate goal is to create high quality software, and we know that high quality software has various key aspects like maintainability, testability, flexibility, and of course, efficiency. So, in this presentation, we will primarily focus on the efficiency aspect. Often, when we think of efficiency, the first thing that comes to mind is speed. So, let's say task A completes an operation in 60 seconds, and we have another task B that completes the same operation in just 3 seconds. Clearly, program B is much efficient than program A. So, how can we bring this kind of efficiency into our software development? One way is through horizontal scaling, where we will have expensive hardware, and even though we buy those, they will have their inherent limitation because of the processing speed limit. So another approach is to harness the power of the multiple processor cores through concurrency. Now, what is concurrency? Concurrency, simply put, involves doing multiple things at the same time, but not necessarily simultaneously. So rather than executing the tasks was sequentially one after the other, what we will do is we will do multiple of those at the same time. To illustrate this further, let's consider an example of a busy chef. So imagine a busy chef in a restaurant has to prepare hundreds of orders, and following traditional approach, he will have to prepare each dish one after the other, only after one completes. So this is not efficient. And through concurrency, what our chef can now do is he can work on multiple orders at the same time without waiting for one dish to finish completely before moving on to the next. So it's just like when we cook rice and dal at the same time, right? And another approach could be hiring multiple chefs. So each chef will work on one dish only, but they will be working simultaneously. So the dishes will be completed faster. So the results orders are completed faster and the restaurant is more efficient. Likewise, in software development, by employing concurrency, what we can do is we can have multiple process and threads handle various tasks simultaneously to improve the program performance. So while we are talking about concurrency, we also need to talk about parallelism. So many people use concurrency and parallelism interchangeably. However, there is distinction between them. As I mentioned earlier, concurrency is a broad concept. It is related with managing multiple tasks which are independent but may or may not run at the same time. Parallelism, on the other hand, is a specific form of concurrency where all the tasks are independent and will run simultaneously, taking advantage of multiple processor cores or CPUs. So it will primarily be focused on performance. And let's say, for example, concurrency, we can have tasks that is divided into subtasks, and the subtasks will could run on the same processor as well based on time slicing or context switching. But in case of parallelism, these subtasks will run on different CPU processors at the CPU cores at the same time. In a sense, it is true parallelism is parallelism, and concurrency includes both true parallelism and false parallelism because of time slicing, context switching, and other techniques. So concurrency is often used in situation where tasks overlap with each other and they do not have to wait for the other tasks to complete. We break down tasks into subtasks so they can be handled by different processor thread. And one thing to note is an efficient program usually has a very high degree of parallelism. So now that we have cleared up the difference between concurrency and parallelism, let's move on to the advantages that it offers. So I have mentioned only the most five important ones. There are others as well, like parallel computing, fault tolerance. So I will explain about these five first. So improvement in performance can be achieved by utilizing the CPU cores to their maximum throughput by implementing high degree of parallelism. And in case of UI applications such as Windows Form, the responsiveness of the UI forms should not be affected by any tasks running in background. By using asynchronous programming, we can ensure that the UI stays responsive and does not freeze. And as for efficiency, so we can have input output operations and CPU bound operations running at the same time, so that increases our efficiency and reduces our idle time. Scalability can be achieved by handling multiple requests across the distributed system. And as for resource management, it is optimized in the operating system and system servers by concurrent handling of tasks through process management, memory management, which reduces the stress on the resources. Okay. Concurrency has its own set of challenges that we must overcome when we implement it. So, as you can see on the screen, I have mentioned top six of those. Race condition and deadlock I will explain in detail in later part of the presentation. So, for now, synchronization overhead. So, when we try to implement lock in our resources to prevent deadlocks and other issues related to concurrency, we might actually get overhead because of the synchronization, so that in turn might reduce the performance instead of increasing it. And we have to take note of how we are implementing that. Another can be resource contention. So in concurrency, we will have multiple tasks, right? So each of those tasks might be trying to access some resources at the same time. So there will be a contention for resource and complex debugging. So if you find debugging a normal application difficult, you might find the undeterministic outcome of a concurrent application almost impossible. The outcome can't be determined easily, and debugging such program, it's very tough. And lastly, we have the limitation mentioned by Amdahl's. So Amdahl's law states that the speed of the program is limited by the fraction of code that can be parallelized. So we have to identify the code that can be parallelized throughout the program and optimize those to their utmost in order to have a efficient program. Now that we have learned about the advantages and the challenges, let's get down to implementation. So let's start with the thread first. A thread insert is a sequence of instruction that is run within the operating system. It is the smallest unit of a process, and it is responsible for only one task. Like it can be network communication, input-output interaction, or input-output operation, or UI interaction. Now, what is multi-threading then? Multi-threading, simply as the name implies, means having multiple thread for various tasks. So multi-threading is about dividing a task into multiple subtasks, where each subtask is independent from the other, and we can have each subtask handled by a separate thread. And with this approach, multi-threading can be used in parallel programming as well. So that depends on the hardware resource that we have available and how well it's implemented in the program. For example, you can consider a quad-core CPU. So, if a well implemented program has four threads, and these four threads can run simultaneously in the four CPU cores, then we can achieve true parallelism. And with that, with the four threads executing simultaneously, the efficiency will be through the roof. So we have to be very careful when implementing these things to achieve maximum efficiency. Now, after multi-threading, another thing that we need to familiarize ourselves with is parallelism. So it can be further divided into data and task parallelism. As the name implies, parallelism is a division of a big tasks into multiple independent tasks, right? So in case of data parallelism, it will be mostly tasks related to data chunks or collection. And as for task parallelism, It can be used to handle a lot of parallel unrelated tasks, and it is very valuable in places where data parallelism cannot be implemented. As I've shown in the slide, we have parallel dot for each and parallel link, or also known as p-link for data parallelism purposes. So parallel for each, it is just a for each loop, but that runs in parallel. And as for p-link, it is an extension of link that runs in parallel. So if those of you who are not familiar with link, uh, it is just like SQL query, but for the backend. So we can use it to query data source or collections or other data structures. And moving on to task parallelism, we have a task library and task class and an async await keywords to handle task parallelism. Let me show the types of tasks that we have in general. So the task method can be further categorized into two types: thread blocking methods, that is synchronous, and non-thread blocking methods, that is asynchronous. So thread blocking methods, what happens when you call them is they will block the calling thread, that the thread that calls them, and wait for the task at hand to complete. And as for non-thread blocking method, they are the opposite of thread blocking method. So they will allow other tasks to happen in background. They will allow other tasks to continue while the actual method that they are waiting for can continue in the background. Some of the thread blocking methods are task wait, task result, and task that wait any, as shown in the screen. Task that wait, what it does is it waits for a task to complete, and task that result, it waits for a task that hand to complete and then returns the result from the task. And task that wait any, it is used when we have multiple tasks, and when it how it works, it waits for multiple tasks to complete, and the first one that is completed, it will return the result of that task. Now moving on to the non-thread blocking methods, we have tasks that when all, tasks that when any, and tasks that delay. So these are just the asynchronous equivalents. So task that when all, it will wait for all the tasks to complete before it returns the result. And task that when any is equivalent of tasks that wait any, just in asynchronous method. And task that delay is a non-blocking method of implementing delay. So after talking about task method, there is one important thing that we need to know. So once you start using asynchronous, you should let it grow throughout the code. So mixing synchronous and non-asynchronous, synchronous and asynchronous code can have various impacts, such as complex errors and unexpected blocking of threads. I will show an example in the next slide, but for now, in the image you can see is for any tasks that you want to do, you can have a blocking and non-blocking version of a method for that task, and it is always recommended to use non-blocking one. So for tasks that wait or tasks that result, that is used to result for a background task, we can use await instead of those. And same goes for wait any, wait all, and thread.slip. So next, next we need to discuss about context. In the slide, I have defined context as something generally refers to the environment or state in which a piece of code or task is executed. It includes various information and resource needed for the code to run correctly. Okay, what does that actually mean? So let's get back to the chef analogy from before. So the chef has to prepare multiple dishes, right? And each dish has its specific ingredient, specific recipe, and cooking time that it needs. So that information right there is the context for that dish. So the ingredient can be something like resource context. The cooking time can be something like temporal context, and the kitchen can be something like execution context. So context is, in short, is just the information and resources that are required for us to complete a task. Now then, what is synchronization context? You can define it as important concept in multi-threading with that captures the current context and handles or synchronizes the thread in asynchronous code or run to sorry in specific part of asynchronous code run on the appropriate thread. So to simplify that, let's say you are going back to the chef analogy. So synchronization context can be a chef. So he will take the dish that he has to prepare, and he will have a context for that, right? Like the ingredients, cooking time, and the recipe. So when the chef is working on that dish, he will have to work in that context. So synchronization context is just like that. When we are working on a particular operation, it will have its own set of context, and synchronization context just captures that context, so that all the thread that run in that operation will follow the context. One thing that we need to note here is that in case of UI-based applications such as Windows Form or old ASP.NET Classic context, they allow only one thread to execute at a time. So please keep this in mind. I will explain it about. I will bring it up a couple of times in the presentation later. So UI application and ASP.NET context, classic context, they allow only one thread to execute in the context. Okay, so next we have configure await. So configure await allows us to control how how the code in an asynchronous method interacts with the synchronizing context. So let's say you have an asynchronous method, right? And in that you will have a await statement, and after the await statement we will have some code block. So we can use configure await to determine whether those code block after the await statement in the asynchronous method should run in the original context that the synchronizing context captured, or they can run in another thread or another thread context. So if we set the configure await to true, it will continue to execute the rest of the asynchronous method codes in the original context that the synchronizing context captured. However, if you configure the configure await to false, the code after the asynchronous method, sorry, await statement in the asynchronous method may or may not run in the original context. So it can move to thread context as well. To explain this further, we have a screenshot of a code block here. So this is an event handler for a Windows form. On the Windows form, I have a button, and when you click that button, this button one click event is called. So on this event, what we have done is we have called a delayed async, which is asynchronous method. And inside that asynchronous method, we have a await statement that just delays the task for 1 second. And in both the method, we have debug write line statement at the end. So when we click on a button, what happens is first it will execute the task delay async, right? So this code block will be initiated, and after that, the main thread will wait for the delay async method to complete. But task.wait is a blocking method, so it will block the current thread in the context and wait for delay async to continue. Then in the delay async, what happens is we have an await statement. So the task delay, it will run in a separate thread, and after it is complete, it will try to continue the remaining part of the code in the delay async, that is debug write line, right? But since it is a UI context, there can be only one thread at a time. And the thread that this debug.write line requires to use, it is already being blocked by this task.wait. So task.wait is waiting for delay async to continue, and delay async is waiting for the block thread to be released so that it can execute this line. This here is a scenario of a deadlock. So this further enforces our concept from earlier that we should not mix synchronous and asynchronous code. Now, how can we handle the deadlock here? So I have mentioned two approaches here. So one is to remove the task that wait completely and move to await the delay async. So this also becomes asynchronous, and this becomes asynchronous, and this will be handled automatically by the synchronization context. So next approach can be configure context, configure await. Sorry. So here we have configure await. Oh, I forgot the false. Okay, so here you can have configure await false, and what happens is that after the task the delay statement is run, it will try to execute the debug.write line, and when it tries to execute that, it will see that the thread in the synchronization context has already been blocked, right? So it will start this task on another thread context. And once this is completed in another thread, then it will return the method back here, and the block thread will be resumed as task.wait will get response from the delay sync. So that is how synchronization context, configure await, and they interact with the context to ensure that the thread runs safely. Now moving on, we have asynchronous programming. So far we have been mentioning asynchronous programming multiple times, but what is it? So it is a technique for software developers to write non-blocking code so that the responsiveness of the application is not affected. So what that basically means is even when we have, let's say, when we start trigger an event, or let's say when we input something in the UI and then send it to the backend, the UI should not stop responding until it receives the response. Imagine a scenario where like you click a button and the UI just freezes until the task is completed. So asynchronous programming resolves that. And we can achieve asynchronous programming usually through the keyword async await and asynchronous methods. So one important thing to note right now is that many people think having async await async await statement in a code makes the code block asynchronous. So that is not true. Consider a asynchronous method where inside the asynchronous method we have task.wait or task.result. So those when the code encounters, sorry, the context encounters that statement, it will block the thread. So in turn, it is no longer asynchronous, but it is synchronous. And going by the same approach, if we do not have await statement inside the asynchronous method, then it will run synchronously because it doesn't have to wait for anything to complete. So it will just execute the code line by line and move on. Uh, uh, Also, in context of UI-based application like Windows Form, uh, what actually happens is the code runs synchronously, but through asynchronous programming, we really get the tasks like order input output network communication tasks, all of those to background threads, so the UI thread stays free and the application is always responsive. So that is also achieved through asynchronous programming. Now we have to talk about is async threading. So then there is a general misconception that asynchronous programming does generate a new thread every time it executes, which is not true. So whenever a thread is sorry, whenever an async await statement is encountered, it is not creating a new thread, but rather it is delegating the awaits the task in the await statement to a thread in the thread pool. So let me show a demo for this. Okay. Okay, so here I have a Windows form in which I have just an async demo button. And on that button click, I have called this event handler. So I have done is I have debugged write line. That is, it will write the current thread ID. So at the beginning, at the beginning and end of the asynchronous method as well. Now, when I call this method, what will happen is it will first await delay one. So it will wait for delay one to complete before it runs delay two. So even though we have asynchronous here, this will still run in a bit of a synchronous approach. So let me start the trigger. Async thread demo. The build is not a debug window. Okay, this is the output. So let me clear this debug. Now when I click on this, main method one begin on trade one, delay begin on trade one. We had 2 seconds of delay, then delay one ended on one, delay two begin on one, delay two end on one, and main method end on one. This is a UI Windows Form application, so it has a UI context, and there is only one thread by default, right? So you can see that we have 2 second delay before these two line, and then only after that delay two is being executed, and also all of these are in the same thread. So if I use configure await false, then what happens is the remaining code in the asynchronous block, that is this debug write line after the await statement, it may or may not run in the synchronization context. So let me run this again. Okay, I triggered it. delay 1 began on 1, 2-second delay, delay 1 ended on 3. So it ended on the last debug write line. It was handled by another thread, and similarly on delay number 2, it was also handled by uh, thread number 3. This is usually not the case, like delay 1 ended on 3 and delay 2 ended on a 3. They both ended up using the same thread, but most of the time they will be different. So it's just a thread in the thread pool. Now you can see that delay 2 is executing only after delay 1. So we can run both of them at the same time using task parallelism. So what I've done is I've created tasks to run delay 1 and another task to run delay 2, and we will wait for both of them to complete before we move on to this line. So now if I run this, so you can see delay 1 began on 1, delay 2 began on 1. We immediately got both the asynchronous method began immediately, right? Earlier, delay 1 began and end before delay 2 began. So now both of these are running at the same time through task parallelism. And as you can see, they both ended on different thread as well. And the main method, it still ended on the thread 1 because the synchronization context uses the main thread for this part of code. Only for this part, after the configure await in this method will be handled by another thread. So that is the demo regarding our configure await synchronization context. The async threading. Let's move on to next slide. Uh, Avoid async void. So there are generally two return types in asynchronous method, and they are tasks or tasks of type T, like I showed in the demo earlier. We had a return of tasks. We had returned a task. We can also return a task of type T, like T is a generic class that can be integer, object, string, or anything. We also have value tasks and value tasks of T, but those are used in only specific condition where the execution of tasks should complete very quickly. So in general, we will be using tasks or tasks of type T. But however, we also have another return type void. So void does not make sense in normal situation. However, it is implemented only for one particular situation, and that is event handler. So it should be made a norm to implement asynchronous void return type only for event handlers and not for the others. Now, why does it make sense for event handlers? So let's say I have a button, and when I click on that button, I do not expect anything to return from it. I just expect some tasks to be performed on backend, but I do not expect any return types from it. Of course, it can return, but generally it will. We do not expect any return type from it. So just to mimic and implement that scenario in our software, we have async void, and if we are to use in any other context beside that, we faced a lot of problem. And the three major one of those are, as I've listed here, cannot await async void. So if you try to use await statement with asynchronous void method when you call it, it will throw an error because we cannot determine whether when an asynchronous void return method will end, as it doesn't have a return type. So it cannot be determined if the task completed immediately or is it still running, and that is a problem for us because we need to know whether the task we had assigned some thread is completed or not. And another is unobservable exception. So if any exception is thrown in the asynchronous void, it cannot be caught in the code. In order to handle that, we will have to go through task scheduler where we have unobservable exception, and that is a very tedious approach, and it's a global solution for our local problem, so it is not recommended at all. And another thing is difficult to test, so as we cannot determine whether it is completed or not, and also many testing framework do not support async void type, so it becomes very hard to test this one. It's not that it cannot be implemented. We can create a custom synchronization context just for async void type of method, but it's much easier to just implement tasks or tasks of type T and work our way through the other part. So that is one thing that we need to note. It's always use avoid async void if we can only use it in one scenario, and that is event handler. Now we come to the thread safety part. So, thread safety is a major concern in concurrency. Race condition it's a situation where multiple threaded program where multiple threads are trying to access the same resource without synchronization. So, for example, here we have thread one and thread two, right? So, imagine you have a resource count that is currently at 100. So, thread one is trying to add 20 to that count, and thread two is trying to subtract 30 from that count, and there is no synchronization, so both of them will try to access it at the same time. So thread 1 will see that count is currently 100, and after trying to add 20, it should be 120, right? So it will try to set the value of count to 120, and at the same time thread 2 will also see that count is currently 100, and it will try to subtract 30 from that, so it will try to set count to 70. So the count will either be 70 or 120 depending on which thread completes last, and that is not valid data. Now our count should be 90 in this situation. So the race condition between these two threads resulted in corrupted data. And another we have is deadlock. So deadlock in simple terms can be defined as a situation where two or more threads are frozen in their execution because they are waiting for the resource that is being occupied by another thread to be released. So in the image, you can see that we have two threads, thread one and thread two, and we also have two resource one and resource two. So thread one wants both resources and thread two also wants both resources. And how can we manage that? So on in an unmanaged unsynchronized situation, so thread one will get lock on resource one and try to get lock on resource two, but at the same time thread two will get lock on resource two and try to get lock on resource one. So thread two will be waiting for resource two to be released by thread two, and thread two will be waiting for a resource one to be released by thread one. So in this situation, both cannot complete their operation because they are waiting for the other thread to release the resource. So they are in a deadlock scenario. Now, how can we ensure thread safety? So we can ensure thread safety through the following five approach. There are other as well, but in this presentation I will be discussing about this. So lock, ineffective use of lock can cause deadlock, but if we use them effectively, they can be a way to ensure the thread safety. So what is lock? Lock is basically like limiting the access of other threads to a resource. So you get you get exclusive access to a resource, and whenever other thread or other process try to access that resource, they will be denied access. And monitor is just a high level abstraction of log, but with some synchronization. So monitor will be able to synchronize the resource among various processes by using timeouts and other synchronization method. And as for threaded join and continue it, so what threaded join does is it waits for the thread that is being executed right now to complete before continuing on with the other task. And tasks that continue with is equivalent of threaded join, but just for tasks that we use in task parallelism. I will give a short demo, so I will just define them for now. And as for timeout, it's a simple concept where a thread should not have access to a resource all the time. It should have it for a limited amount of time, and after that, we have to either unlock the resource, or we have to handle how the timeout operation will continue. So let's start. Let's look at a demo. On race condition. Okay. So here I have created a race condition scenario where there are two threads and both of them will be trying to uh, contend for the console write access. So they will both contend for console write. One control, right? One has print star and another has print plus. So when I start this, you can see that we have 3 plus followed by 2 star and then a plus. So it is not both of them are contending for the access, sorry, right to log to console. So it is not synchronized, and sometimes this thread 1 runs gets the access and sometimes thread 2 gets the access, so they will be able to write their output, right? And in this situation the output is never consistent. So if we want to synchronize these two, we can do so using our join, continuate, log, and monitor. So let's start with log, and in the program, log method. Okay, so I have created a locker object, and when we have lock on that object, only the one with the lock will be able to execute the code that is protected by locker. So we have implemented locker in both the print star and print plus, and instead of did, sorry, I forgot something. Okay, instead of using thread, I have used tasks here. So it's just running. It's just a implementation of tasks instead of thread. The process will run the same. There are no differences. So let me run this program. Oh, close this. Okay. Okay. So after implementing the logger, only one of them is allowed access to the code block inside the locker, right? So first in this scenario, the task one, which is print star, was able to gain lock of the locker. So first we have print start followed by print end. However, it is not necessary that it will always print star first. It will depend on which task gets the locker access first. So if we run it a couple of times, we might see a different scenario. Okay, currently it is always tax one, but it is not required that tax one will always be the one to get the first access to locker, as both of them are running in parallel. Okay, so next one we can check using monitor. So monitor is just like log. We will have enter a log when we enter we will also have a locker object, and when we enter a locker object, we will restrict the access to the code inside that part. So we have restricted it. So only if you have access to locker, then you will be able to enter here. And if you do not have access to the locker, then you will wait for the other thread to release that locker. And we must also implement this monitor.exit locker, because after you are done with the code, you must always ensure that the monitor is executed. Sorry, the resource is freed. So here print star is followed by print plus. So we do not have a race condition. And similarly for thread join and let me cut this. So in this part, this is using thread join. So we have started thread one and we have thread one dot join. So this part here, it will not execute until this thread has completed, and only after that we will resume here. So it is a method to synchronize the threads. So let me run it in debugging mode. Oops. Okay. First thread one ran. Thread one was started. Thread one join. So until this completes execution, we will not be able to reach this point. Now that we can see the output. Okay. And thread that continue it, it's just it's same like the thread that join, but instead of thread that join, we use continue it. So task 2 will continue only after task 1, because we have task 1 that continue it. So it will be the same. Now we can check on deadlock. So deadlock demo. Okay, first we have a deadlock scenario. So here you can see as well, I have started both threads, but I did not implement a join statement until both thread were started. So thread one will start, thread two will start, and only after then we will wait for both of those to complete. So in the in the methods that the threads are executing, we have log one and log two. So we have two logs, log one and log two, and both the thread are trying to get both the logs before they continue to this part. So if I run this, so you will see that thread 7 acquired log 1. So the thread 1 that we are running, it is running on thread thread ID 7, and it has acquired log 1. And here it is attempting to acquire log 2. But at the same time, thread 2 ran and it acquired a log on log 2. So thread 2 is has ID 8. So it acquired log 2 and it is attempting to acquire log 1. So both of them are waiting for the other thread to release the log. So they are in a deadlock scenario. Now we can handle this using different approaches, but here I have used monitor with timeout. So what this does is the monitor will get the log, but just for 1 second. So after that 1 second, it will release the log, and if required, then it will again try to get that log. So as mentioned earlier, we have when we get a lock from using monitor, we have to release it at the end. So first it will try to get lock one, then it will have that for 1 second, and during that 1 second, it will also try to get lock two. But if the 1 second is passed before it acquires lock two, then lock one will be released, and it might get lock two, but it won't have lock one. So it will continue to try to get both the locks until it gets them. So we have the same method in acquired lock too. So you will see that these two thread will. So it has acquired lock one, it has acquired lock two. It is attempting to acquire. Sorry, I did not change that. Okay. So every 1 second, they will lose the lock that they already have while trying to access another lock. So this will continue until one thread acquires both lock and the other doesn't have both of them. So as you can see, this might lead to thread starvation depending on the timeout that you use. So we need to carefully consider these parameters when using monitor. So as you can see here, thread one acquired lock one, attempted to lock two, attempted. So threaded acquired lock one, thread 8 had acquired log 2 and thread 7 had acquired log 1, and when thread 7 was attempting to acquire log 2, its time under log 1 was expired, and then thread 2 attempted to acquire log 1 and it was able to get that. So thread 8 was done, and after that both the logs were free. So thread 1 acquired both log 1 and log 2 and it was also done. So you can see that we will have some thread starvation on this approach if the configurations are not proper. However, the deadlock is handled. Okay, now going back to the presentation. So we have concurrency management. So let's say you start a task that does a lot of background tasks, but in the middle you remember that you may have to make some order changes before you continue that task, and you decide to cancel it. But so we do need a feature to be able to cancel asynchronous tasks as well, right? But they are different from our normal approach. So how cancellation is done in in concurrency is through asynchronous token source and asynchronous token. So cancellation is like a signal. There will be a sender and there will be a receiver. The sender or the source will be cancellation token source, and the receiver will be cancellation token. That is for the definition. Just keep that in mind, and I will show a demo later on. Next is progress reporting. So when you have multiple like asynchronous tasks running, like you could have even thousands or millions of them running at the same time, right? So you would want a progress report on that. In C Sharp, we have a progress reporting interface that allows us to fire an event whenever something happens. So We can use that to report our progress. And lastly, we have exception handling. So exception in concurrency works differently than exception in our normal synchronous code. Let's say in a concurrent program, you can have multiple threads, right? So all those threads are running asynchronously, and say 100 of them throw exception. And now these exceptions, they are not propagated directly to the calling method. So first they are collected and stored in the aggregate exception, and that aggregate exception is returned to the calling method. And this aggregate exception, however, can contain a lot of nested exception. Like inside the exception, there will be inner exception, and inside that we will have another inner exception and such. So we have another method called flatten, and what it does is it creates a collection of uh, exception, and instead of going through all the nested except inner exception, it will create a collection of just the inner exception, and we will be able to handle all the exception locally instead of going through each nested object. So those are our concurrency management concept. And now let's move on to our final demo, where what I've done is I have implemented some of the concept that we have discussed throughout this presentation. Let me switch it back to concurrency demo. Okay, so this is the Windows form. I have input this start, cancel, sorry. There's loading GIF and this progress bar as well. But I will not start with all of them at once. First, let's start with what happens when you click on start. So right now, what I have is I will put the thread to sleep for 5 seconds, and nothing else. So this is just the at first we will just have this start. So if I run this and click on start, you will see that the loading image, sorry, GIF, it stopped. So that is because, as I mentioned earlier, in UI, UI projects like Windows Form, there is only one thread at a time, and that is UI thread. So when I click on this and the thread is put to sleep, there are no other threads. So this UI itself will stop responding. I cannot drag it. I cannot do anything on it. So that is not a desired behavior. So we will implement an asynchronous approach to this. So in the asynchronous part, uh, so I do not want to show this loading GIF at the beginning. So I will just hide it at the beginning, and I can show and hide it from the code on the backend. So in this asynchronous method, what I've done is first I will show the loading GIF when we receive a button click event. And after that, I have this delay here and a message box that shows that 5 seconds has passed. In this delay method, we are, sorry, 3 seconds have passed. We are delaying the thread asynchronously by 3 seconds. And you notice here we are getting a green error, right? So that's because I have not awaited this delay. So what happens is if I run this code as it is without the await statement, it will trigger the delay event, but it will not wait for it to complete and simply go to this next set of instruction. So as soon as I click, we will get that 3 seconds have passed. If I run this and start loading appear, 3 seconds have passed. We did not wait for this task to complete. So if we await that statement, now we are mentioned that we have to wait for this task to complete before executing with the rest. So start, 3 seconds have passed. So you saw that after I clicked on start, I was still able to use the UI, right? Because that's because we are using the await statement, and it what it does is it frees the UI context to do other tasks while we wait for this task to complete. And also now the message box shows only after this task is completed. Now let's move on to a more advanced approach. So now what we want to do now is we want to have let's say we will have a set of cards. We will get a set of cards and process that card by sending a request to the web API. So uh, this will be a demo of the task that when all implementation. So let me, is it stop? Okay. So first, let me show what I've done in the web API. I just created a simple web API. In it, I have a helper class that will generate a random number between 0 and 1. So it is just a random number generator, nothing special about it. And in that process card that we will be calling, so we will pass a card. And in that card will either be processed approved or will be rejected, and determination for approved is if the random number is generated is greater than 0 0.1, then the card will be approved, otherwise it will be rejected. So it's just a simple logic, nothing, there's nothing much going here. But as you can see from here, 90% of the card will be approved and 10% will be rejected, right? And we will return the card and whether it was approved or not in this value. So this is what we have done in the web API. Now we need to make changes on the web form so that we can send a request to the web API. So what I've done here is this is the URL where the web API is hosted. You can check this by going to the debug setting. Yeah, it's hosted in 44393. So that is the URL that I have used here, 44393, and the slash API, that's just route control. What I have mentioned that API that cards, if we receive the route API that card, so only then will we redirect to this one. So okay. Now this is a get card. So get card method, what we have done is we have simply just generated a list of numbers in string. So you can see parallel 16 here, right? It just means that we will have a string of 16 digit like this, that of maximum 16 digit like this. We can have 0 0 0 0 0 1 0 0 0 0 2 and something like that. So the cards will just be numbers like those, and we can determine how many cards we want by passing the amount of card to generate. So in this method we have nothing, just a for loop that will generate us a number which we will treat as card number, sorry. So at first I want to get 5 cards, and after I get those 5 cards I want to process them as well, right? So in this process method what I have done is for each card that we receive we will need to send a request to the web API. So it's just a JSON that serialize and HTTP client post async request. So post async because we are trying to asynchronously send request, and the API URL that we have declared here. So in short, what it is doing is it is just sending the card that we have passed here to the web API to check whether it was approved or not. And this for is for all the cards that we want to process. And the tasks that when or how it works is we have all these tasks that are running in asynchronous, right? So we want to wait for all of them to complete before we return the process card method. So once all of those tasks are completed, then we will go back here and then execute the rest. So if I run this for 5 cards, oh sorry, I need to run the API as well. I will start typing non-debugging concurrency demo start. Okay, now okay, the API is starting. Waiting for it to load. Okay, the API is up. Now we can check the output of the web API here. So when I start, it completed in 1.8 seconds, and the cards that were processed were 14023. You can see that they are not in the sequential order 0, 1, 2, 3, 4, 5, because we are running the tasks in parallel. So any one of them can complete first. And also, I forgot to mention earlier, in the process card, we have a delay of 1 second, right? But we processed all five tasks in just 1.8 seconds. So we did not wait 1 second for each task to complete, and all of them were running parallel. Okay. Now let's improve this further. So instead of mm, we have, okay, let me show the problem first. So if I do this, so this is just a demonstration that all the tasks are running in parallel, and even though card processing takes 1 second, when we process 500 tasks using task parallelism, I need to okay, check if the API is up. Okay, API is up. Now, typically what we would think is we have 500 requests and 500 cards that need to be processed, and each card takes 1 second to process, right? So if we start the tasks, it's normally it would take 500 seconds to complete, but we just got it in 3 seconds. That's the power of parallelism. And you can see all of those were processed in the web API. Now, you might have noticed, but the GIF loading, it was not responding for a bit after I click to start. So let me increase the request count, and let's do this again. I have set it to 15,000 requests now. So 15,000 cards will be processed when I click on start. So you see that the loading icon is not coming up for a while. It is being processed. It will take a while, but it is being processed. So the reason why the loading GIF was taking time to load was because we have this get card method, which is synchronous, and we also have this for each uh, for each uh, iteration that will create the request, but it is still running in synchronous method. So when before we get to the actual process card, we have this thing that need to run 15,000 times, and this thing that needs to run 15,000 times. So because of that, okay, you can see it completed in 48 seconds. So because of that, the initially until this synchronous task was completed, the UI was not responding. So what we need to do now is we need to make it asynchronous. So for asynchronous, what I will do is, let me comment this part. So it's the same method. It's still the same get card as earlier. Get card as earlier. So all I've done is I have taken all these tasks that we were doing synchronously and put it inside a task run. So this task of generating the cards, it will be delegated to separate tasks that will run in the background, and in the meantime we will be able to do other tasks. And for the same as we did the same for the for each loop that we were using to process generate a request to send to web API. So instead of current for each, we have implemented lazy loading. Sorry, not lazy loading, sorry, we have moved the tasks into we have moved the for each iteration loop inside a task so that it will also run in parallel. And when this is running in parallel, we are also awaiting for them to complete. So as the tasks are created, they will start hitting the API, and some of them will complete, and some of them will still be running, right? So when we wait for all tasks to complete here, some of them might already be completed, but we will not get a return from here until all of them are completed. So in this part, what we did was we simply moved the synchronous part and assigned it into parallel tasks. So now if I run this again with the 15,000, but instead we have await here because we are using we are implementing is that asynchronous method. So if I start now, let's check the API. Okay, it is up. Now, as soon as I hit start, the zip loading is already there, and I can use the interact with the UI as well. So the synchronous part that we were that was causing UI thread to be blocked earlier, we have resolved that with this part. Now moving on, it will take a while to execute. So in the meantime, I will make other changes. Oh, so since I made 15,000 requests, it is very taxing to my memory and CPU. So please give me a moment. I have not implemented the tasks yet, so that is the reason why I cannot cancel it right now. But we will be able to check that later. So you can see my CPU is at 100%. Okay, let's wait a moment. Okay, 59 seconds. Okay, so this is a problem, right? When I am passing too many requests at once, it is causing the web API to be overloaded, and the request generated from our end is also high. So we are going to throttle that. By throttling, we means that we will have only a certain number of requests requests sent to web API at a time, and for that one, we will be using semaphore slim. So many of you might have already learned about semaphore during our bachelor's course or whatnot. Semaphore slim is just C# version of light implementation of that. So in this one, if you check the code, so previously we in get card we had delegated it to tasks and the for loop was still there. It's still the same. We have not made any change on get card, but in get process, what we have done now is instead of the for each loop that was under a task, we will be implementing a semaphore. So we have a semaphore, and on it we have 1,000, right? So we will only allow 1,000 requests at a time. And as for this part, this is just lazy loading. So instead of for each loop, we are using lazy loading so that when for each card that we have to process, we will create a request, but we will wait for the semaphore before we send that request. So if the semaphore is already full, we will wait for it. But if we have a slot empty in it, then we will enter this part. We will send the request to web API, and after it is complete, we will have to release the semaphore. So it's just the implementation of semaphore using lazy loading. We have not changed other part like the task to when await. It's still there. And now when I run, in order to get a better view of the output, let me limit the semaphore to 3. So the request will be processed in a batch of 3. And since we are each process, sorry, each card processing takes 1 second, and we are doing 15 cards, so they will be handled in a batch of 3. And the output is 5 seconds because we have 15 and we have done it in 5 batch, so each batch was 1 second. So that is implementation using semaphore, but we just checked it for a small number. So let's check for the number that we were getting issue earlier. So when we were passing 15,000, we were getting earlier error, right? So let's pass 15,000 again. But this time we have a semaphore. So with resource throttling, it should not be CPU intensive. Let me close this one first. Okay. Web API started, and I will click on start. UI is responsive, and we should start seeing the request. So yeah, I'm still able to use the UI trail because we are doing it in a batch of 1,000. So only there will be only 1,000 requests at a time, and that can easily be handled by our server as well as our system. So 22 second, and there was no issue with our UI. So that's a plus plus. Now that we have implemented semaphore, let's move on with cancellation. Actually, let's first check progress report. So get cards method, it's the same as before, no change on this. As for process card, we had implemented semaphore, that is still the same. And inside the semaphore, previously we didn't, we only had HTTP request, right? So what we have done now is we have added some calculations here. This is to calculate the percentage of tasks complete. So we have task result here, right? Task result will be incremented every time a task is completed, and percentage is just the number of tasks completed by the total number of tasks. We will multiply that by 100, and we will round it off into an integer value. So it's just a percentage value calculation, nothing much there. And you might see that we have made a change here. So previously we were just using, let me show that code. So we had it in a single statement, await, sorry, no, return await HTTP context, right? So it would wait for this to complete and return that. But now what we have done is we have assigned it into one variable, and we await the completion of that, but we return that variable. So it's just dividing us one line code into two line, not much different. And one new change that you will see is in progress card, we have a new variable called progress. So let me comment this out. Okay, so what I've done is I have added a new variable. Sorry, we have this progress bar here already, right? So what I've previously it was invisible, but now what I've done is we will show it, and when we start the button click event, we will show it, and after the button click event ends, we will hide it again and set it to 0 for next run, preparing it for our next run. So in the method itself, get card 3000, that's not different. We had our wait here, we had our process card, not different. The only thing different is this. So earlier I mentioned that we have a interface in C# that allow us to report our a fire event whenever something occurs, right? So this is that interface, implementation of that interface. And what I've done is whenever I report something with this progress report variable, it will trigger this report card processing progress. So it will be an integer type, and I I have passed it here in the process card. Process card I progress type integer type. So what I've done here is progress dot report percentage int. So it is of type int. So I'm just reporting that the percentage has been updated. So when I report that a percentage has been updated, we have configured it to call this report card processing progress. So in that method, all I've done is I have updated the value of this progress bar. So progress bar value equal to percentage. Now, if I were to trigger this, you can see that the progress is being reported as tasks completes. So as tasks are completing, the progress is being reported. So there is one issue with this. We are reporting the task completion as it completes. So say if we have millions of tasks, this will be reported a million times, and we do not want that. So let's change it. Instead of reporting every time a task is complete, we will change it so that the reporting is done once in a regular interval. So for example, once every 1 second, once every 2 seconds. So in the same part, nothing has changed. I still have progress. I still have semaphore, but the part that okay. So for process card, if we check on our previous implementation, we had this calculation done inside the semaphore with the where it would be calculated every time the request was completed, right? So we do not want that anymore. So what we will do is we will leave the semaphore as it was before. In the semaphore part, we will just make the request. But outside, you will see that we have assigned the task that went out to the variable, and what we are doing here is we are using when any. So when any means that whenever one of these two tasks completes, it will return that. And as long as report task is not completed, it will not be returned. So every second this will return a task, and every second what it will do is it will check whether the return task was response task or this delay task. And as long as the report task is not completed, it will not be returned, right, as we mentioned. So it will return a delay task, and that will not match. So inside this while loop, we just move the calculation part from there to over here. So completed tasks would be whatever is the tasks that have been completed. So we can get that with the parameter called is completed. So all tasks will have is completed, is faulted as their parameter, and we will get the count of tasks that have completed so far. And the percentage calculation is the same: completed tasks by number of tasks that need to be processed into 100 for percentage conversion, and mapped around for integer value. So this while loop will run as long as all the tasks are not completed. You can simply get that from understand that much from this part of code. And what we are doing is we are doing 1 second interval reporting. So this report in this part in this the code inside this while will run once every 1 second. Mm, this report 100, what I've done is at the end, while like once we come out of this loop, the report task will have already completed, right? So I will make the report 100. If I do not do this, I will show you in the output as well. I will be processing 3000 cards. Web API, it's running. Okay, Web API is up. When I click on start, okay, the process and the request will be in process. And now, once every 1 second only, the progress will be reported. And because I did not set progress report 100 at the end, so when the while loop last ran, it was at this percentage of completion, and after that, the while loop exited. So the part inside this report, it was not hit once the response task was completed, and that is the reason this has not reached 100%. And that was the reason why I had this here, because it doesn't look good when the progress bar is not filled. Sorry, I have OCD. Okay. So that was for reporting in this interval of 1 second. And lastly, we have to check the implementation of cancellation. So far, we have not implemented cancel tasks. So let's get on to that. Cancel event. Okay. So when we click on cancel button, this event will be triggered, this cancel event. And let me comment this out. So most of the code are same. What we have added is we will be adding a new cancellation token source. So cancellation token source will be called when we click on the cancel button, and when we click when the cancellation token source invokes a cancel method, the cancellation token will cancel the tasks, asynchronous tasks that are running. So if I go here, you will see that I have initialized a new cancellation token source every time the start button is clicked, and that is being the token generated by that is being passed into our process cards. Orders are still the same, and this part cancellation token source implements I disposable, so it must be disposed always. So that is why after this code completes its execution, we will be disposing the code. Okay. So in the progress, we will be passing the new cancellation token, right? So by default, it will be default, or it might not have a value sometimes. So we will be using default value as its default parameter, and all we do is we pass this token in the asynchronous post request. That's all. Nothing else is changed. This part is still the same, and these are still the same. Oh, I forgot to mention one thing earlier. So after assigning the task terminal to a response task variable, we are awaiting that one time here and one time over here, response task. So even though we are awaiting this two time, it does not mean that the response these tasks will run two times. It's just mean that we are checking whether the tasks have completed two times and awaiting the output. It's not running the tasks two times. Okay, so with that out of the way, the rest are all same. We just pass the token to the post async HTTP request. So when we click on the cancel button, we will use the cancel method in the cancellation token source. This question mark is just for handling the null situation because it can be null. So that's just null exception handling. And now when I run this, oh, I need to close this. Okay. Okay, it started and the API is started as well. So if I start the progress, okay, it's the API. I will cancel. The operation was cancelled, and no more requests are being sent to the web server as well. And I think I forgot to mention one thing. So when we cancel the token, it will throw a task cancellation exception. So in order to not cause throw a system pop-up, we just have this task exception handling message box where it will show that the task was cancelled. If I do not have this, I will start it and cancel. Did I not rebuild? Tasks that cancelled. API started. Start. Requests are coming in. Cancel. Seems like the code change is not being reflected for some reason. However, if I do not have this, there will be a system pop-up saying that there was an error or something. And with that out of the way, we have done so. What we have achieved in this demo is we did a simple synchronous asynchronous demo and how that impacts on the UI thread. And that is, it stops responding in synchronous approach. And another was we used the asynchronous we call the web API asynchronously, and we tested the power of the task.winall, task.parallel, and we also used throttling to control the number of requests that is sent over and impact on our the stress on our resources. And we also implemented a progress reporting, and finally we have implemented task cancellation, but we have still not checked on exception handling. So for that, I have created a simple aggregate exception handling method here. Okay. So in this, all I'm doing is calling this asynchronous method, and when the task ID is 1, it will throw error. When the task ID is 3, it will throw error. And when task ID is 2, it will just delay for 1 second and return. So I have created these 3 tasks, and I have exception handling here and here. So let's see what happens. This one. Close this. Okay, we got the exception. So if I highlight this, we can see that we have 2 errors, right? instead of like having to handle the try catch over here, both of these are being thrown here in the aggregated exception. So I can see both of them in at the same time and handle them if necessary. Sorry, was that? Yeah, inner exceptions. So this is the aggregated one. So we can see both the exception here, and if required, we can handle both of them here, or we can handle them as this. So if I throw it over to the main calling context, we can have ex.flatten. So after using the flatten, the two exceptions that we had in the inner exception, those will be generated in the context, and we can simply use this as a object. So continue, and in the output you will see we have error on task 1 and task 3. So that is how we handle error on multiple threads. Okay, so we are done with this, and next one. So some of the books and people that I learned from regarding this for this presentation was especially I think it was number two, Concurrency in C Sharp book, but number one, it is one of the best to learn out there. So it is the parallel programming by the first one. It's very advanced. So before that, I recommend that you get started with some basics and then go through some intermediate level books like this Concurrency in C Sharp cookbook by Stephen Cleary. You could also follow Kevin Goose and David Fowle on their GitHub and Medium pages. And if you want to get started on Async, you can start with this. And that was all for my presentation. It's been a long one. Thank you for bearing with me throughout all this.